Okay, hello, good afternoon, everybody. Today's lecture is going to be from home, as I explained, because our lecture hall is taken by a conference in the Banach Center. But this is a one-time thing. So next time, I invite you again to the lecture hall at IMPAN, room 321. Today, I want to prove to you a basis theorem. I hope I can do it in one go. So I already advertised the following lemma. And you have to excuse me because writing on my laptop is much harder than writing on a professional graphic tablet that I have at IMPAN. But anyway, we will manage. So the claim is that I can define the set, I call it BE. This is a set of following elements in my conpath algebra. So these are classes of the following elements. I have chi, alpha, beta star, and I demand that the end of the path alpha is equal to the end of the path beta. Otherwise, it would be zero, you see, because the beginning of the path beta star is, of course, by construction, the end of the path beta. So in order for this chi alpha beta star to be non-zero, I have to have this condition. And of course, alpha, beta are arbitrary finite paths in E. So if you want, then alpha beta star is a particular path in is a particular finite path in E bar, the extended graph. Okay, so the claim is that this is a basis of the absolute conpath algebra. Okay, and I want to make another disclaimer that this lecture is very difficult to give because I'm going to explain things that are very elementary, very non-exciting. On the other hand, combinatorially complicated. So it's one of these things where there are no great ideas to explain. You just have to sit down and verify some cases and compute and have a closer look. So this is a boring type of a lecture. I don't like such lectures, and it's particularly tough on me to show you all these special cases and convince you that it works. On the other hand, this is an absolutely fundamental theorem. This is a basis theorem. You can prove almost nothing. You cannot even work out the examples I showed to you without knowing what the linear basis is. Okay, and the proof is relatively straightforward, but as you can imagine, it is lengthy. Okay, so let's start with proving this lemma. This is in fact the most difficult part of the whole proof, because our goal is to prove the relative version of this lemma, right? So the theorem I want to end up with today is to have a set for CKXE, so for the X relative conpath algebra. But let's first prove the absolute case. Oops, but I need a pen, not an eraser, to do it. So first, it is really straightforward to see that this set BE spans the conpath algebra. Right, because remember, the conpath algebra is nothing but the path algebra of the extended graph divided by the ideal generated by just one type of a relation. You just say that, aha, if I have chi E star, chi E, then it must be the same as chi the end of E. Okay, so of course the linear basis of KE bar would be by construction given by all finite paths in E bar. So this means that you could write words in alphas and beta star, and you could alternate. You could have you can have a non-start part to the left and start to the right, or the other way around. But with this condition, we are able always to shift any start element to the right. Okay, so at the end of the day, the only thing that remains will be chi's labeled by paths such that the first part of the path is in E, and the second part of the path is in E star. Okay, so that's the only thing that happens. Maybe I will draw a picture. Here we have some T of alpha. This is path alpha. This is path beta, and T of alpha is equal to T of beta. And now we take a path beta star, and this is the path alpha beta star, and that's what we consider. Okay. And if we would consider things which are more general, like alpha, gamma star, and then beta, then somehow this part would be eaten up until there would be nothing which is non-start to the right of something which is start. Yeah, because this relation allows us to shift any start edge to the right. I mean, we don't really shift it; we simply collapse it. We kill it. So either things do not match and we multiply to 0, and then really everything dies, or things match as I drew in the picture, and then, well, you just get you replace E star E with TE. Okay, so maybe I will be a bit more specific. So imagine that beta begins with E. So here we have some alpha. Okay, let's just say that here I have some E star, just one edge. Okay, and beta begins with E. All right, so beta is equal to E beta prime, or simply just to E. Okay, so if beta is equal just to E, well, this is what happens. But in fact, remember that the end of E is the beginning of E star. That in fact is more correct to draw it this way. And then instead of having such a loop at the end, we replace it by the end vertex of E, which is this vertex. So then this just becomes alpha, and this whole thing vanishes. Anyway, if you just think about it for a while, it's really obvious that it always holds. I mean, you will not have any expressions of the form with something start being on the left of something non-start by this effect. Okay, so I take it that you accept it, right? But it's clear that B spans the conpath algebra. Everybody happy with this? No objections, so I go on. So now, of course, it remains to prove the linear independence. So to prove the linear independence of this set BE, we consider, and this is a nice idea. This is a pretty original idea. I took it from the book. Today, everything I'm telling you is from this book, Levi Path Algebras by Gene Abrams Ferrara and Mercedes Siles Molina. So to prove the independence of BE, we consider the following vector subspace I denoted as VE, and this is the vector subspace of KE bar. And I want just this part of KE bar, which is spanned by, well, something very similar to BE. So I denote it as BE tilde, because I'm basically writing the same expressions, except that there's no equivalence class sign. So chi alpha beta star with T alpha equal to T beta, and alpha beta being any finite paths in E. Okay, so if you want, you apply the canonical quotient map, this one here, and you transform this BE tilde into BE, all right? But now, because I view it as a subspace of KE bar, I know that this element, that the set is linearly dependent. Okay, so BE tilde is linearly independent by construction. Okay. Because basis elements of KE bar are all chi's labeled by finite paths in E bar. So I'm just choosing specific type finite paths in E bar, and I take their linear span. This is my new vector space, and this is its basis. Okay. And now the idea is that we will turn this vector space VE into an algebra, but it will not be a subalgebra of KE bar. So this is the trick. We will turn this VE into an algebra, but this will not be a subalgebra of a path algebra KE bar, even though it's a vector subspace. Okay. And then we'll construct a map from CKE, from the cone path algebra of E, into this VE, and we prove it to be an isomorphism. And then it will be clear that the set PE is indeed a linear basis of the cone path algebra CKE. Okay, so let's do it. So we will now define an algebra structure on VE. And we do it by defining the bilinear form. So we define a bilinear form VE cross VE, VE. And I can define a bilinear form by saying what I do on basis elements. And this is a very important formula. So I take chi alpha beta star, one typical basis element, and chi mu star, another. And by definition, I set them to be the following. This is chi alpha mu prime mu star if mu is equal to beta mu prime, and it is chi alpha beta prime star mu star if it happens that beta is mu times some b prime. And it's zero otherwise. Okay, so this is a very, very important formula which we are going to use for quite some time now. And to prove that V is an algebra given by this bilinear form, it suffices to prove that this bilinear form is associative. So to see that the bilinear form defines a multiplication on VE, it suffices to show that it is associative. Well, which means, and I'll keep writing the quantifiers. The quantifiers is for every alpha, beta, mu, gamma, delta, which is a finite path in E. Okay, we have to prove the following equation, namely that if I take chi alpha beta star with chi mu star, and then I add chi delta gamma star, it must be the same as taking chi alpha beta star with the linear form applies to chi mu star, comma chi delta, sorry, gamma delta star. Sorry, I have to correct it, otherwise I'll get confused. It's CD, so it's gamma delta star. Gamma. Okay, so this is what we need to prove. And this will require some tedious work. But on the other hand, you know, that's something that one should do every now and then. It's even the most brilliant mathematicians not only juggle ideas and brilliant tricks, but every now and then do very dirty computations, in particular computer-assisted computations. So every now and then you just have to do the dirty work of some tedious computations so that you have you are really in touch with what's going on. So that's why I don't want to skip it. Okay, so well, we are computing it, computing both sides, all right? So when I compute the left-hand side, my computation is as follows. Let me just rewrite it. Chi alpha beta star, comma chi mu star, close the linear form, chi gamma delta star. So what I'm going to do, I'm going to simply use this formula, you see. I'm going to use this formula and simply put here a bilinear form, comma chi delta mu, and so on and so forth. Okay, so this is a very simple plug-in substitution. It's just that it gets very quickly very complicated. But the first step is easy because I basically rewrite it, and now I have what? The bilinear form of chi alpha mu star mu bar with chi gamma delta star, and this is again if mu is equal to b beta mu prime, or we are going to have chi alpha beta prime star mu star with chi gamma delta star, and again this is if, well, not again, I mean this is when beta is equal to mu beta prime, and of course it's 0 otherwise. By the way, I forgot to draw a picture of how you should read this formula. So forget for a second about this chi gamma delta star. Why somebody did come up with such a formula? You see, the thing is the following. So here you have your path alpha beta star, okay, and now you have a path gamma. Sorry, no, mu star. Of course, if it so happens that the end of beta star is not the beginning of mu, you'll just get a 0. But assume that this is not the case. And if indeed these the end of this path is not the beginning of this path, then nothing happens. It's just concatenation. But things that we are interested in are the following. You see, what if mu is equal to beta mu prime? So what does it mean? It means that I write as part of mu, I write beta, and then I have some mu prime remaining. But now I have to redraw the picture, because remember, the end of beta is in fact the beginning of beta star. Okay, so now more accurate pictures the following. I have alpha, I have beta star, I have beta, and now out of beta I have coming out mu prime and then mu star. Okay, so basically I have a certain bubble on my way, and this bubble needs to be collapsed. I'll have some, instead of looking at the path alpha, beta star, beta, and then mu prime, mu bar, this is what we will do here, right? We could go alpha, beta prime, mu prime, mu star. If we had no relations, this is what happens in the path algebra of the extended graph. But we want to mimic what happens in the conpath algebra. So all such bubbles which are of the form beta star beta must be collapsed. Okay, and when I collapse it, you see I just erase this bubble, and what do I have? I have alpha, mu prime, mu star, alpha, mu prime, mu star. You see, and exactly the same effect happens when it's the other way around. Mu is part. So this was what? This was when I took that beta is part of mu. But what if mu is part of beta? If mu is part of beta, so let me erase it. Okay, this is mu. So if beta is equal mu beta prime, this means that b star is equal to beta prime star mu star. Okay, so this means that here we have some mu star, and here we have some beta prime star. Okay, but then the reasoning as before, we'll have a bubble, because you will see that in fact the beginning of mu is the end of mu bar. So in fact mu starts from here, and we also know, sorry, in fact, yeah, sorry, I will draw it. So I have alpha, I have mu star, I have mu coming back here, right? And then I have what happened to on mu star must go here. No, mu is already mu is already drawn. So after mu I just have mu star. Sorry about it. So here I have just a mu star continuing. I'm confused. I somehow lost my beta prime star. Let me try it again. Okay, this picture is surely correct. Right, I have mu star, and I say that beta is mu beta prime. So this means that beta star. Oops, I picked on the wrong side. This means that beta star is equal to beta prime star mu star. So you see, yeah. So I know why I couldn't make heads and tails out of it. We should have corrected me. I didn't reverse the order. It's beta prime star mu star. Okay. So this is why the picture didn't make sense to me. So the first part of beta star is beta prime star. The second part is mu star. And as before, in fact, this vertex is the same as this vertex. So new star starts here, and you collapse this part into a point, and you end up with alpha, beta prime star, a new star. And this is exactly what we have: alpha, beta prime star, new star. Okay. Sorry about this confusion. One error in writing something, and we get into trouble. So that's why this formula is completely natural. This is exactly what you would expect it to be if you are hoping at the end of the day for an isomorphism between the conpath algebra and this auxiliary algebra VE. I repeat, it's very important. VE is a vector subspace of KE bar, right? So VE in KE bar only as a vector space, not as an algebra. Okay. Well, and now I'm afraid that we have to continue computing. So we have to now write down what it is, substituting at two places formulas for the bilinear form. And now this is going to be a way more complicated. So please bear with me. I hope I will manage to continue this equality here. So there will be a lot of cases. And I'll just copy what I have in my notes, and then I'll try to explain. You see, this is like one of these things I'm drawing for you on the pictures. It's nothing but combinatorics, but this is a daunting combinatorics, and it's very easy to get confused. Of course, I am just applying all the time this formula, which is our key formula for this lemma. But now to apply this formula, of course, I have to, this is now my new path. This is, and this is my other new path, all right? And only with these substitutions, I can use the formula, okay? But if you do so, you will arrive at the following list of cases. So first, you will have chi alpha mu prime gamma prime delta star, and this is if mu is equal to beta mu prime. So I just repeat the case I already have. But now I have some other condition, and I must have that gamma is equal to nu gamma prime. Now it's chi alpha mu prime star delta star if, well, the first part is the same because we are considering mu equal to beta mu prime. We are unraveling this bilinear form. But now the second condition is that it is mu that you can express as gamma mu prime. Oh no, I clicked the wrong button and I erased everything. Ooh la la. Okay, but I will not rewrite everything. I will just rewrite for you this case. Okay. Chi alpha mu prime gamma prime delta star if mu is beta mu prime and gamma is mu gamma prime. Now I have chi alpha mu prime star delta star if again mu is equal to beta but this time nu is written as gamma nu prime. Okay, and I have three more cases, sorry. So now we're going to consider the other case, namely when beta is equal to mu beta prime. So then we have chi, and this is a little bit surprising because it's a little bit shorter. We have chi alpha gamma double prime delta star. And now we have, as the second condition, is that nu beta prime is equal to nu beta prime gamma double prime. Sorry, I wrote something nonsensical here. Sorry, it's about gamma. And gamma is equal, gamma is equal to nu beta prime gamma prime, and it's annoying heavy spurious marks. Okay, and you see, and this is a gamma double prime. This is because of all these substitutions, right? Remember that at a certain moment when I write out my formula, my path which plays, say, the role of alpha in this formula. So I have a path which plays the role of alpha in this formula, but this path is given already by concatenation of two other paths. So when I do such substitutions, I'll simply obtain these weird looking things, right? But this is just saying that that the end of the other path, which is just this part, is inside my path gamma, so it can be complemented to some gamma double prime. Okay, and because I will use gamma prime above, I use this gamma double prime here. So don't be surprised; it's just nothing but substitution. And similarly, again, the first one is the same. Beta is equal to mu beta prime. But now we have it sort of the other way around, that in this path, mu beta prime, gamma sits inside. So you can write mu beta prime as gamma times some lambda. Right, because it's the same story as before. We have mu beta prime at one end and we have gamma at the other end. And either mu beta prime is a subpath of gamma, or gamma is a subpath of mu beta prime. And then we can always complement it uniquely by some paths, respectively gamma double prime and lambda. And of course, zero otherwise. Now, please forgive me for not verifying for you step by step that this is really the correct formula for plugging. It's much better when you just do it yourself, okay? And now we compute what happens on the other side. Yeah. So now we are computing chi alpha beta star bilineared with the bilinear form of chi mu nu star chi gamma delta. And this is the easy part. That's just a simple substitution. I take the formula for bilinear form, and then I still write on the left bilinear form with chi alpha beta star. Okay. So here I'll have chi mu gamma prime delta star if gamma is mu gamma prime, chi alpha beta star. Now we have the other way around, mu is equal to gamma mu prime. And then what I write here is chi mu prime star delta star, and zero otherwise. Okay, so as before, I'm going to rewrite it into some monstrous formula, and I'm wondering if I can fit it on this page. Probably not. I'll go to the other page. So because then what I'll write on the next page will compare what's written on this page. And it will be just a lot of reshuffling in substitutions, a lot of combinatorics. But for the time being, let me write this out. So this is equal to the following thing. Again, first two cases are if gamma is equal to mu, if gamma is equal to mu gamma prime, I have two such cases. Okay, but then the second one is that mu gamma prime has beta as a subpath, so it's equal to beta lambda. And then what we obtain is just chi alpha lambda delta star. Now, if it's the other way around, if mu gamma prime is a subpath of beta, then we can write beta equal to mu gamma prime, and let's say beta double prime. And then we'll have chi alpha beta double prime star delta star. And the other two subcases are for mu equal gamma mu prime, and in the first case we've got mu equal to beta mu prime, so beta is a subpath of mu, and then we consider the other way around. What happens when mu is a subpath of beta? So when beta is equal to mu beta prime, yes, and then we'll have respectively chi alpha mu prime star delta star, and here will be chi alpha beta prime star mu prime star delta star. And finally, of course, we have 0 otherwise. Okay. So this is really, honestly, can trust me, this is nothing but plugging in the bilinear product formula. You just have to be very careful when you do it because of the stupendous notation. And I'm not going to explain it any better. You should just sit down with a pen and paper or a piece of chalk and a blackboard and verify it for yourself. Last week, it took much of my night to do all these verifications. And I'm not going to bore you to death with this. But what is more exciting is that indeed, because on the face of it, they don't really look it. If I compare page number 3 with page number 5, I mean, these are not obviously the same formulas. Oh, and I forgot here to write a formula. But please, if you see something wrong, speak to me. Don't leave me alone. If I make a mistake, just yell at me. Of course, here I should just have written something, and the something is chi alpha lambda star delta star. But now we are going to make the following clever observation. If you look at these chi's here on this page, and then you look at chi's here on that page, what do they have in common? What is strikingly similar everywhere here? Can anyone tell me? Any guesses? No, you see, alpha and delta do not figure in these relations on both sides. There's no alpha and delta. You see, you have lots and lots of Greek letters, but you have no alpha and delta. It's gone. Yes, and also when you look at the position, alpha is always the last piece of your path, and delta star is always the final piece of your path. Okay, it's the same in both cases. So this means that in order to compare these two expressions, first we can forget these chi's. It doesn't make any difference whether we compare paths or linearly independent elements labeled by paths in our graph out in our path algebra. So in order to compare these two expressions, we're going to do things. First, we skip chi's, and secondly, we skip alphas and deltas. Okay, and this will give me something much simpler to compare. All right. So let me write it like this: comparing these two expressions boils down to comparing the following. Well, if you go to this first expression, we'll have mu prime gamma prime for mu equal to beta mu prime and gamma equal to mu gamma prime. I'll try to write the vertical bar so that I don't go too far. We just have gamma double prime for beta equal to mu beta prime and gamma equal to mu beta prime gamma double prime and lambda star for beta equal to mu beta prime and mu beta prime equal to gamma lambda. So this is what we compare with the following expression, which comes from the second computation. And here we've got lambda for gamma equal to nu gamma prime and mu gamma prime equal to beta lambda. Then we have beta double prime star for gamma equal to nu gamma prime as before. But now we have that beta as mu gamma prime as a subpath. So that there's mu gamma prime beta double prime. And finally, beta prime star, mu prime star for mu equal to gamma nu prime. So now gamma is a subpath of mu, and mu is a subpath of beta. So beta is mu beta prime. Okay, and now let me convince you that these two expressions come from where they should come, namely from the first and the second computation respectively. While you surely understand why I skipped writing 0, I mean, there's no point of comparing 0 with 0, it's just equal. But I should have here, I should compare here four cases. So how come that I skipped one case? Well, if you look carefully, two expressions just coincide on the nose. And I think that in the second computation, This is the expression which comes, I think, as the third one. Because yes. Okay, so that's the third part. So let's look into the third expression, this one. Okay. So I have mu equal to gamma mu prime and beta equal to b and u equal to beta mu prime. Okay, and now let's compare it, I think, with the second expression in the first calculation. Yeah, you see, this is the same. Mu is equal beta mu prime and mu is equal gamma mu prime. Mu is gamma mu prime, mu is beta mu prime. That's the same thing, okay? And now, of course, we have alpha delta in the same position, so I just have to remember what happens with mu prime, and we've got here clearly mu prime and mu prime star. Now, when I go to this expression, it's the same. It's mu prime star. So these, out of this comparison of 5 cases, 2 cases obviously coincide. Okay. So we are left with comparing just 3 cases. Well, you should be careful with this otherwise, because you really have to see that somehow these if conditions of in one computation really agree with if conditions in the other computations. So then otherwise we'll agree as well. Okay, but that's what we are going to do right now. All right, and now you see what is left. We have if we forget the case number 3 and number 5, we are left with case number 1, which is lambda. Case number 2, which is beta double prime star, and it agrees. And finally, we consider beta prime star, mu prime star, and that's it. Okay. And in the same way, I can just read out from the other expression, right? So I will start with mu prime gamma prime, and let's see. I have mu prime gamma prime. Then this case I skip. Then I have gamma double prime and lambda star. And indeed, I have gamma double prime and lambda star. Okay, are you with me? But now, in order to make this comparison, well, I'm afraid we have to split it into some subcases. Okay, so it's not easy to see it so directly, and the splitting into subcases comes from the following troublemakers. You see, this is a troublemaker here, because when I say that gamma is a subpath of nu beta prime, well, I have to say, is it a subpath of nu already, or is it really a subpath of nu beta prime? So there are just like 2 separate cases, okay? And here the troublemaker is, of course, this expression. Again, are we just saying that beta is a subpath of mu, or are we just saying that beta is a subpath of mu gamma prime? Okay, these are these 2 special cases that we have to consider. And in order to write it carefully, I'll use 1 page for rewriting this one and 1 page for writing that one. So let's start with the left. So right now, splitting into subcases, we obtain the following. Okay, let me just write it and then explain. It says mu prime gamma prime if mu is equal to beta mu prime and gamma is equal to mu gamma prime. Next. Well, the first one changed. I'm just writing gamma double prime is beta is equal to mu beta prime, and gamma is equal to mu beta prime gamma double prime. And now we have these two split cases. I have lambda star twice. Yeah. So here I have if beta is equal to mu beta prime, mu is equal to gamma mu prime, and lambda is equal to mu prime beta prime. So you have here like conjunction of three expressions. And the second case, which is obtained from this splitting into subcases, is, well, of course, the beginning is the same, beta is equal to mu beta prime. But now we write gamma is equal to mu gamma prime. And beta prime is equal to gamma prime lambda. Okay, so let's see how we obtained it from the previous expression. Okay, so I'm concerned with this case, all right? So I have, well, beta equals mu beta prime, we've got it. But now we have nu beta prime equals gamma lambda. Nu beta prime equals gamma lambda. So I want you to recognize these two subcases. Well, if I have that gamma is already a subpath of nu, well, then I can write nu equal to gamma nu prime, all right? And then I will have some leftover. How should I do it? Okay, let me draw this. This is my path mu, and this is my path beta prime. Okay, and I know that this is equal to gamma lambda, but I don't know where gamma ends. Does it end in beta prime or does it end already in nu? All right. So first case is when gamma already ends in nu. So the first part of nu is gamma, and then I have some nu prime, all right? So then you have a certain leftover. This is, if you don't just notation, this is not really a condition, right? You say that this is equal to nu prime, beta prime. This is your lambda. Okay, this is something which complements. Remember that lambda. Wait, no, sorry, I'm wrong. This is no. This is not a notation. Lambda was simply defined here as something which complements the path gamma to nu beta prime. So by definition, lambda is the path which complements the path gamma to the path nu beta prime. Okay, so in case gamma ends inside of nu, right? What happens is that this nu primes times beta prime must be equal to lambda. Okay, and this is exactly what I wrote over here. All right, so now let's consider the other case when gamma ends further out. It goes beyond. So this is gamma. Okay, it ends already in beta prime. Okay, so then what we can do, of course, I can write gamma as a nu gamma prime. This will be my gamma prime. Yeah, that's just uniquely determined by nu and gamma. And then what happens with beta prime? Well, beta prime, so this is what I wrote. Well, beta prime is by design. Well, actually, beta prime is already given. Beta prime is already given. Sorry, but now it's decomposed into gamma prime. Okay, and something else here. And the something else is again lambda. So you agree, beta prime starts here, says gamma prime times something, and I want to convince you that this is indeed lambda. And why is it lambda? Well, because lambda is by construction something which complements gamma to nu beta prime. You see, so this must be lambda, okay? But now we can write beta prime as gamma prime lambda, you see? So these are the subcases. I warned you that there's going to be some daunting combinatorics. And now let me not repeat the reasoning and do the other case. I'll just copy it. But I already pointed to you where it comes from, all right? Now this will come from splitting, what, I erased something instantly. Should be mu gamma prime, yeah. It comes from splitting this into two subcases, all right? In exactly the same way. So let me just copy it. So now the first two cases will be interesting. We'll have lambda, and this is for gamma equal to mu gamma prime, mu equal to beta mu prime, lambda equal to mu prime. And now again, we have gamma is mu gamma prime. This is unchanged. But now here the conditions are beta equal to mu beta prime and gamma prime equal to beta prime lambda. And then I just rewrite the other two conditions. So I'll have beta double prime star if gamma is equal to mu gamma prime and beta is equal to mu gamma prime beta double prime. And I'll have beta prime star mu prime star if mu is equal to gamma prime and beta is equal to mu beta prime. Okay, we obtain it in exactly the same way. All right, so now I have a daunting task to compare these two things. And of course, you should bear in mind that these are different, these Greek letters stand for different paths in one expression and in the other. So we should really look at how they are defined in each of the calculations and then reconcile the notation. But I claim that now reconciling the notation, we conclude that these expressions are identical as desired. So let me write it and then really do it. Reconciling the notation we see that these two expressions coincide as desired. Okay, so let's try to see if we really see it. Okay, it would be good to have them one by one. I have to recall how we do it. To find some common points. Okay, maybe we start by considering the special case when because it looks simplest. Let's really take that mu is equal to beta mu prime and gamma is equal to mu gamma prime. Okay, and let's see how these things compare. So when I go now to the other expression and try to find it, mu equal to beta mu prime. Where is it? Yes, I have it actually at two places, and yes, I have it at two places, and I have two subcases here, but the result is exactly the same. Okay. So you see, this can be compared with these two cases, right? Because here I have mu equal to beta mu prime and gamma equal to nu gamma prime. Am I correct? It's yeah, gamma equal to nu gamma prime. So we definitely want to consider this case, but we also want to consider that case. Luckily, it speeds up the same thing. So by reconciling the notation, we have to prove that lambda is in fact always equal to mu prime gamma prime. So we have to prove that lambda is equal to mu prime gamma prime. Okay. So let's see if we can do it. Well, actually, in this first case, it's done because we already know that lambda is equal to mu prime. You see? Ah, sorry, it's mu prime gamma prime. Okay. So in the first case, we have to prove that the nu prime is equal to gamma prime. Okay, let's see. I will rewrite these equations on the next page. So we have because I have to remember them. Okay, so but the first part is sort of stands. It's gamma is mu gamma prime, and mu is beta mu prime. This is what we have. Yes, and oh. I highlighted the wrong thing. This is sorry. This is beta equal mu beta prime. Mu equals something is only at this place. So sorry. You guys really should correct me when I make a mistake. This is beta equal mu beta prime, not mu equal beta mu prime. So I just compare this. Yes, it's mu equal beta mu prime. It's only one case. Okay, so we have to prove that gamma prime is equal to nu prime when I have all these equations. And where do I have the definition of so gamma is equal to nu gamma prime, of course, and mu is equal to I don't remember how it went. Why do we conclude that yeah, I warned you that this is a tough cookie. this combinatorics, and I think I'm doing it correct, because in my notes it's just saying reconciling the notation, we conclude that these expressions are identical as desired, which is true. I spent much of the night a week ago really doing that. But now let's see. I mean, we somehow have to manage. Gamma is mu gamma prime. And mu is beta mu prime. Okay. Okay. And here I get lambda, and here, so this was my mistake. Sorry, there's nothing to prove. I made a typo here. This is gamma prime. Okay, then we are done, because we have mu prime gamma prime, and this coincides. So this case coincides with the first case over here. These are the same expressions. Okay. Now we'll have the standing assumptions that beta is equal mu beta prime. Yeah, that beta is equal to mu beta prime. Okay. So if you want, here you can conclude that this part is beta prime, because mu and beta are given. So, and beta prime is defined as the unique path that extends mu into beta. Okay, so this must be beta prime. Okay, so let's just compare the second case. I have lambda, and now I have to compute what really lambda is. Okay, so this is. I think that I have to make it into the following equation. So you see, when I have this equality, in order somehow to compute lambda, I have to multiply it by mu. Okay, then I have that mu gamma prime is, which is equal to gamma, by the way. So mu gamma prime is equal to beta prime lambda. Okay. Sorry, is equal to nu beta prime lambda. And this should allow me to determine what lambda is. Again, how do we do it? I hope again I didn't make any typo. Lambdas gamma nu gamma prime beta nu beta prime gamma prime beta prime lambda. That's okay. And yeah, so this is where we are. We have to compute lambda. Okay, so I have let me again take it to the other page. Yeah, this can be erased. This is the case which is done. And I basically copy this second line. Okay, so gamma is nu gamma prime. No surprise here. Gamma is nu. Beta is mu beta prime. And gamma prime is beta prime lambda. Okay, so we immediately concluded, okay, let's multiply it by nu. So I have that gamma is equal to nu gamma prime is equal to nu beta prime lambda. And now I think we need to draw something to make, no. Again, I hit the wrong button and I erased it. I'm so sorry about it. So gamma is nu gamma prime. Beta is mu beta prime. And gamma prime is beta prime lambda. Okay. So now we have that this is in fact equal to nu beta prime lambda. Okay, and now let's draw a picture to make heads and tails out of it. What have we got? We have mu nu and okay, we have alpha beta. So we have beta star. Okay, then we have mu. Then we have nu star. And then we have gamma. Okay, so these are these four important pieces. And now I'm saying that first, nu is a subpath of gamma. Okay, so let me rewrite it. Actually, maybe. You see what I need to compute, and of course you didn't correct me again. This is not mu, this is lambda. What I need to compute is lambda, and I want to see it on this picture because lambda is uniquely determined, and this will be the outcome of what we have in this case. So let's see, lambda is something, so gamma prime is something which uniquely complements nu to gamma. So here, this part is say gamma prime, okay? And this part is nu. It's getting awfully complicated. I now vaguely remember that in fact this is not something I did by pictures, but by this kind of calculations. So now I'm a bit confused. I have to compute the lambda, that's for sure. And lambda is something which does what? It complements gamma prime. So it is inside of gamma prime. Oof, maybe I will enlarge this picture. So inside gamma prime, I have what? I have here is lambda, and here is beta prime. Why do they coincide? I want to see what I want to prove is that yes, because I wanted to compute it in terms of, okay, I see it in terms of one calculation. Sorry. Now this is what we have in the second calculation, okay, and we know that the result is lambda under these conditions, and here the result is gamma prime. But in the notation we have over there, what have we got? We have the same thing when it comes for beta. So beta is equal to mu beta prime. But now we have gamma equal to mu beta prime gamma double prime. Okay, so that's the situation we have on the left hand side. But now you should realize that gamma here is equal to nu beta prime lambda, here is equal to nu beta prime gamma double prime. So comparing these two equalities, we conclude that lambda is equal to gamma double prime as desired. You see on the left-hand side, we say, aha, we take nu beta prime and we complement it uniquely to gamma. And this is called gamma double prime, and that's the result. And here what we have is the following. We have as equality gamma equal nu beta prime lambda. So lambda is defined as the unique path extending nu beta prime to gamma. So that's the same definition of lambda and gamma double prime. So again, we have checked that all coincides. Okay. So the second line here coincides with the second line there. All right. So I'm wondering, maybe I should leave it at this, and you trust me that you verify the other cases much in the same way, because at least I would like to finish the proof of the lemma. So let me maybe first finish the proof of the lemma, and then if time permits, I will also tell you why these two guys coincide. So let's do it. So now assume that we already have checked that these two expressions coincide. All right. So this proves the associativity. So hence we infer that VE is an algebra with a multiplication defined by this bilinear form. And now we do the following nice argument. Namely, we view the concave algebra, so viewing the concave algebra CKE as the universal algebra given by generators and relations. I think this was discussed during recitation class. Universal algebra given by generators and relations we can check that the formula which is the following. I take an element, say chi p in CKE, and I map it to chi p in VE, and I take my P to be from the generating sets as either a vertex, or it is an edge in E, or it is an edge in E star. Okay. So we can check that the formula given by this assignment defines an algebra homomorphism. Well, indeed, we can just check how it behaves to these relations. If I write f of the class of chi p times the class of chi q, where both p and q are from this generating set, so pq in here, then we can check that this is equal to the following. You have just two cases. It's chi of a vertex tp and the Kroneker's delta pq for p in E1 star and q in E1. And we have chi pq delta Kroneker's delta tp sq otherwise. You can directly check it from the formula, and then you realize that this is indeed, it defines a homomorphism, because when you have the universal algebra given by generators and relations, and you want to define a homomorphism on this algebra, well, you just apply your map to, I mean, you don't know whether you have a map yet. You make your assignment from the generators, and then you check that when you follow these assignments, the relations which are given in your universal algebra are satisfied in the target algebra into which you make this assignment. And this is exactly what happens here. If you look at the Kohn path algebra as the universal algebra given by generators and relations, well, these are the generators. These are chi p's, where p is either a vertex or an edge in E1 or an edge in E star, okay? And then you must have the path algebraic relations. So all that it means is that we have concatenations when the end of one path equals to the beginning of the other path and zero otherwise. And then you have this one special relation when it so happens that P is equal to Q, all right? When P is equal to Q, and P, sorry, P, no, what am I saying? Something is wrong here. Well, we're interested in just one case when P, yes, when P is from E1 star. Okay, so it has to be, so there's a typo. It has to be that the P star is the same as Q. I forgot the star. Yeah. So we must have that that P is equal to Q star. Sorry. So this is the only, yeah, that's what I want. Okay. P is equal to Q star, and then we have the end of Q taken here. Right, because the only additional relation that we have in this path algebra of the extended graph, E bar, is that we say, aha, when I have chi E star E, this is the same as chi T of E. Okay, that's the only relation. So when I look here at this formula, I'm interested in the special case when P is equal to Q star. Okay, when P is equal to Q star, otherwise just zero. When P is equal to Q star, then we actually have something stronger, right? Because well, when P is equal to Q star, then obviously the end of P is the beginning. The end of P, yes, must be must be the beginning. No, sorry. When p is equal to q star, okay, then we obviously have that the end of p is the beginning of q. That's satisfied, right? Because the beginning of q star is the end of q, so it's the end. Yeah. So you must have that t of p is equal to s of q, right? But then you don't just get chi of pq. You don't get chi e star e, because we collapse chi e star e into chi te. So this is why I have this relation. Okay. So this is like strengthening of this path algebraic relation, and this is the Kohn path algebra viewed as the universal algebra by generators and relations. So if you just follow this assignment, and you see that what you end up with is what you've got really on the right hand side, you're done. These relations are satisfied. So F is indeed well defined. And while that's not so obvious that this is the case, you would have to go back to the formula, and I'm not going to do it. It's some boring combinatorics, and which I'm going to skip. But you look at the formula. You basically look at the multiplication on VE. You see, what you really have to look at is to look at multiplication. This bilinear form tells you how to multiply basis elements. Okay, so this is your multiplication table, and now imagine that you consider a number of cases, right? You so you take this formula, but now you take alpha to be p, beta is just the end of alpha. It's just a vertex. It doesn't bother us. Okay, and then here you take mu. Sorry, you take well. Let me write mu first. Mu is just the beginning of a new star, and the new star must be your no, sorry. I think I take yeah. Depending on where P and Q is, you just say if both P and Q are in E1, then you take then you also take mu to be something trivial. It's a vertex. It's the end of mu, and then you take mu equal to Q. So this is what happens when P and Q are and E1. And these are these edges, and then you plug it into this formula and compute what you've got. You also have to take into account what happens when P is a vertex and Q is a vertex. So basically, you have like 9 cases to consider. So consider 9 cases and plug it into this multiplication table. And when you do that, but this is much easier than the other combinatorics. When you do that, you immediately conclude that this is in fact correct. This is what you've got on the right hand side. All right. So now we have this algebra homomorphism, but finally observe that f of VE, the set we're interested in, is just equal to B E tilde. Okay. So this means that, and remember, this is by construction the basis of VE, all right? And you immediately conclude that B is linear independent, because if the image of a set is a linear independent set, then the set itself, of course, by linear map, then the set itself is linear independent, okay? So B E is linearly independent because B tilde is a basis. So this way we are done with the proof, and that was the key idea. The key idea to remember, in addition to these boring calculations, is that we want to define a map from the conpath algebra to this artificial, or if you're not artificial, auxiliary subalgebra, auxiliary algebra VE. Okay. And then the map itself is kind of tautological. You basically, it's like a variation of identity map. But the crucial thing is that we prove that this map F exists by arguing with the universal presentation of the conpath algebra. But if you want to use this argument, you must map not into a vector space, but into an algebra. So we have to equip VE with an algebra structure. And this was this horrible combinatorics that we're verifying, but VE is indeed an algebra's claim. And with this algebra structure with which we equipped VE to become an algebra, in fact, this assignment has these beautiful properties that if you have chi p multiplied with chi q, I mean here the classes, you do this assignment and you realize that you end up exactly where you should end, which is on the right hand side. Okay, so yeah, because here of course you can just multiply it out, and this is f of the class of chi pq modulo this condition. All right, but then in the special cases this class will allow you to do this collapsing. So you see that everything rock and roll. So once by this hard combinatorics you prove that this is an algebra, by the universal presentation you prove that this map exists, and it's of course by construction an algebra homomorphism, and then it's just an obvious observation because it's basically the identity map. Of course you have that f of b is equal to b e tilde. So the elements that I said BE must be linear independent, okay? Because this is the linear independent set. And that's it. We prove that this is a basis. So, and my time is over, so I'm going to stop here. This combinatorics, although it took me like, I don't know, half an hour to do it, it's 1.5 pages of calculations to check these 9 cases, but this is very easy. This is very, very easy. And as an exercise for you, I leave for you verifying that also the other 2 lines coincide respectively. Okay, so we checked like half of this combinatorics, the other half remains to be checked, but I hope that by now we have got the hang of it, how you are doing this checking. And I'm doing it for you so that you appreciate that this is not so completely trivial. I mean, this combinatorics here is of course straightforward. It's a no-brainer, but and it is tedious and boring, I agree, but it is subtle. It's not something that you can just look at and see, obviously these 2 expressions are the same. You have to look at it a little bit harder. Okay, so if there are no questions, let me stop here, and we see each other at the recitation class at 4:30. Any questions? Okay, I don't see any questions, so see you in 26 minutes. I stop recording.